In this video, we'll see a quick application of Markov chains to analyzing a randomized algorithm for 2SAT. Let's recall the 2SAT problem. We've got some formula, phi, which maybe looks something like this. That is, it is the AND of a bunch of clauses. Each clause is the OR of two literals, and total there are going to be n variables and m clauses. Our goal is to decide whether or not phi is satisfiable, that is, whether or not there's a way to pick values true or false for each of these n variables so that phi becomes true. Here's a randomized algorithm for 2SAT. It looks a little bit like the algorithmic LLL algorithm that we saw for KSAT earlier, but it's slightly different, and we're going to be able to analyze it with a Markov chain. So here's the algorithm. First, we're going to pick any assignment sigma naught to be our starting assignment. Doesn't matter which. Then, for t equals 0, 1 up to c times n squared, where c is some constant, we're going to do the following. First, we'll check to see if our current assignment satisfies phi. If so, we'll just return it. In that case, phi is satisfiable, and we know because we've found a satisfying assignment. Otherwise, there's some unsatisfied clause, so let's just choose one of them arbitrarily. Doesn't matter how we choose it. And suppose that that unsatisfied clause contains variables xi and xj. Then we're going to update our assignment, sigma t, and we're going to obtain sigma t plus 1 by, with probability 1/2, flipping the variable xi, and otherwise flipping the variable xj. And then we're just going to repeat. And if we finish this whole for loop without ever finding a satisfying assignment, we're going to give up and return not satisfiable. So that's the algorithm. It turns out that this algorithm actually works with high probability. That is, if phi is not satisfiable, then the algorithm will always say so and return not satisfiable. On the other hand, if phi is satisfiable, then the algorithm will return a satisfying assignment with high probability, in particular with probability at least 1 minus 1 divided by 2 to the c over 2, where c here is the same constant that we had in the definition of the algorithm. It should be pretty easy to see that if phi is not satisfiable, this algorithm will always say so. So let's put a check mark next to that first bullet point. For the rest of this video, we're going to focus on proving this second bullet point. So let's suppose that phi is satisfiable. We are going to define a few useful random variables that are going to help us analyze the algorithm in that case. So since phi is satisfiable, let's fix a satisfying assignment, sigma star. If there's more than one satisfying assignment, it doesn't matter which one we choose, just pick any of them and call it sigma star. Now, for t equals 0, 1, 2, and so on, let's define a random variable x sub t, which is equal to the number of variables in sigma t that agree with this satisfying assignment sigma star. Notice that if x sub t becomes equal to n, then that means that we've, in fact, found sigma star. All of the variables agree. So now I claim the following. I claim that with probability at least 1/2, x sub t is going to be equal to x sub t minus 1 plus 1, conditioned on sigma t minus 1, the assignment that we already have. Further, if x sub t is not equal to x sub t minus 1 plus 1, then it's going to be equal to x sub t minus 1 minus 1. Let's see a quick proof. Suppose the clause that was violated in sigma t minus 1 looks like xi or xj. You can check afterwards that the argument that we're about to give doesn't care if these guys are going to be negated or not. So for simplicity, let's just assume it looks like that. Now there are a bunch of cases. In the first case, the value of xi in the assignment sigma star is equal to true, and so is the value of xj. Notice that because this clause was unsatisfied in sigma t minus 1, we're going to have sigma t minus 1 of xi equals false, and sigma t minus 1 of xj is also false. So now what's going to happen in our algorithm? We'll choose one of these two variables at random to flip. In either case, a false is going to turn into a true, and we're going to increase our agreement with sigma star by 1. So in this case, the probability that x sub t is equal to x sub t minus 1 plus 1 is equal to 1. Okay, so in this case, that certainly satisfies the claim. 1 is bigger than a half. And now let's move on to case 2. In the second case, let's say that in sigma star, one of these variables is false. So now in this case, what is the algorithm going to do? It's going to choose one of these two variables at random to flip. With probability a half, this false will become true, which will decrease the agreement with sigma star, because sigma star was false here. And with probability 1/2, this false will become true, which will increase the agreement with sigma star, because sigma star was true on xj. So in case 2, the probability that x sub t is equal to x sub t minus 1 plus 1 is equal to 1/2, and the probability that x sub t equals x sub t minus 1 is also equal to 1/2. Once again, this is consistent with the claim. Finally, we can look at the third possible case. That's the one where sigma star of xj is false and sigma star of xi is true. And then exactly the same logic will show that these conclusions still hold. So in that case as well, the claim holds. And these are the only possible 3 cases. So that proves the claim. Check. So now here's a question for you. We've just defined these random variables x0, x1, x2, and so on. And we've defined xt in terms of some stuff that happens to come before xt. Because this is a video on the applications of Markov chains, you might expect that x0, x1, x2 is indeed a Markov chain. No, it's not a Markov chain. No. Okay, so the xi's do not form a Markov chain. However, we can define a Markov chain that is related to them, which will be useful. So here are some more useful random variables. So I claim that there exists a Markov chain, y0, y1, and so on, so that the following things hold. First, y0 is going to be equal to x0. Second, for all t greater than or equal to 0, yt is bounded above by xt. And finally, the yt's form a nice Markov chain. In particular, they form the Markov chain given by this diagram here. Reading through these bullet points, these say that if yt minus 1 is not equal to 0, so if it's somewhere between 1 and n minus 1, then the probability that I increase by 1 is equal to 1/2, and the probability that I decrease by 1 is also equal to 1/2. On the other hand, if yt minus 1 is equal to 0, then the probability that I increase by 1 is equal to 1. That's just deterministic. Intuitively, the reason that such yi exist is that the probability that xt increases by 1 is always at least 1/2. And so if we change that to be exactly equal to 1/2, then intuitively, it's not going to make the x sub t's any bigger. That is, we're going to end up with some y sub t's that are at most x sub t. To prove this formally, we can construct the random variables yt as follows. So as before, we're going to choose our assignments sigma I, as in the algorithm, and our variables x sub I as before. And then we're just going to define y0 equal to x0, and then we're going to define y sub t as a function of sigma sub t minus 1, y sub t minus 1, and x sub t as follows. First, if y sub t minus 1 is equal to 0, then we'll set y sub t equal to 1. This takes care of the requirement at sort of the left-hand side of the chain. And then we're going to do the following. So let's define p sub t to be the probability that x sub t is equal to x sub t minus 1 plus 1, conditioned on sigma t minus 1. And notice that by our claim earlier, p sub t is going to be greater than or equal to a half. Now we're going to define the behavior of y sub t. So if x sub t happens to be equal to x sub t minus 1, then we're just going to define y sub t accordingly. So y sub t is going to be equal to y sub t minus 1 minus 1. On the other hand, if x sub t is equal to x sub t minus 1 plus 1, then we're going to employ some further randomness. So we're going to flip another coin, and with probability 1 divided by 2 times p sub t, I'm going to set yt equal to yt minus 1 plus 1, and otherwise yt is going to be equal to yt minus 1 minus 1. Intuitively, what we're doing here is sort of picking up the slack of the extra probability that might happen if pt is strictly greater than 1/2. To see why this is a sensible thing to do, let's compute the probability that y sub t is equal to y sub t minus 1 minus 1, conditioned on y sub t minus 1. Well, okay, so there are two possible outcomes. Either x sub t is equal to x sub t minus 1 plus 1, or it's equal to that minus 1. So with probability 1 minus p sub t, this event occurs. X sub t is equal to x sub t minus 1 minus 1. And so in that case, y sub t is also going to be equal to y sub t minus 1 minus 1. So in that case, the probability that this outcome happens is 1, conditioned on that event. On the other hand, with probability p sub t, this event is going to occur. And in that case, the probability that y sub t is equal to y sub t minus 1 minus 1 is equal to 1 minus 1 over 2 pt. So let's put that here, 1 minus 1 over 2 pt. And now we can see why we chose these particular expressions here, because this simplifies nicely to be exactly 1/2. Similarly, we can compute the probability that y sub t is equal to y sub t plus 1, conditioned on y sub t minus 1. And this is equal to 1 minus p sub t times 0. That corresponds to this event happening, in which case this event definitely does not happen, plus p sub t times 1 divided by 2 pt. That's this event occurring here. And once again, this simplifies to be equal to 1/2. Now, we've defined these y sub t's in a very convoluted way, right? It involved sigma t minus 1, yt minus 1, and xt minus 1, and we introduced some new randomness along the way. However, if we ignore everything about sigma and x and just focus on the y's, that is, if we forget about all of this stuff that we did, and we also forget about sigma t here and x sub t, and we forget all about that, and let's forget about this computation that we did, and forget about that, then what we're left with is just this marginal distribution on y sub t's. Here. And if we just look at this marginal distribution, forgetting everything about the sigmas and the x's, then this has all the properties we wanted. In particular, it's a Markov chain that looks like this. Okay, so that proves this claim. We can find these random variables yi. Why did we want to do this? Well, the fact that y sub t is less than or equal to x sub t means that it's more pessimistic to look at y sub t. That is, if y sub t is greater than or equal to n, that's going to imply that x sub t is greater than or equal to n, which is going to imply that sigma star is equal to sigma t. That is, if x sub t is greater than or equal to n, then actually x sub t must be equal to n, which means that all of the variables in sigma t agree with sigma star. However, this Markov chain y sub t is much easier to reason about. So that's what we're going to do now, and we're going to show that this is reasonably likely to happen reasonably quickly. Okay, so let's analyze this Markov chain, why not, y1, and so on. So here's a lemma. I claim that if we have this Markov chain that looks like this, then for all I, the expected number of steps until y sub t equals n, that's this here, conditioned on any starting point at all, is at most the expected number of steps until yt equals n, conditioned on starting at the leftmost side of the chain. Intuitively, that makes sense. And that this expectation is in fact equal to n squared. So let's prove this lemma. Let r sub I be equal to this expectation. So the expected value of the minimum t such that yt is equal to n, conditioned on y naught being equal to I. Then we can write down a bunch of relationships between these ri's. In particular, r naught is equal to 1 plus r1. That's because if I start at 0, then with probability 1, I'm going to take one step, and then I wonder how many more steps do I need to take starting from 1. By similar reasoning, r1 is equal to 1 plus 1/2 times r naught plus 1/2 times r2. That's because if I start at 1, no matter what, I'm going to take one step. With probability 1/2, that step is going to go towards 0, and then I have r0 expected steps left. On the other hand, with probability 1/2, that step is going to go to 2, and then in expectation I have r2 steps left. This same logic works for any ri, so we have ri is equal to 1 plus 1/2 ri minus 1 plus 1/2 ri plus 1, all the way up to rn minus 1, which is equal to 1 plus 1/2 rn minus 2 plus 1/2 rn. Finally, we have rn is equal to 0 just by definition. If I start at n, then I have 0 more steps left until I get to n. So now we want to know, what are these ri? One observation is that here I have n plus 1 variables, r naught up through rn, and I also have n plus 1 linearly independent linear equations. So I know that there's a unique solution for these ri. I just need to find it. So I claim that that unique solution satisfies r sub I is equal to r sub I plus 1 plus 2i plus 1. We can prove this by induction on I. As a base case, we have that r naught is equal to r1 plus 1. That's just from over here, and also happens to be exactly what this thing is when you plug in I equals 0. So for I equals 0, this is true. For I greater than 0, let's suppose by induction that ri minus 1 is equal to ri plus 2 times I minus 1 plus 1. And then using this equation here, we have r sub I is equal to 1 plus 1/2 ri minus 1 plus 1/2 ri plus 1. And now plugging in this for ri minus 1, this is equal to 1 plus 1/2 ri plus 2 I minus 1 plus 1 plus 1/2 ri minus 1. And if you do a bit of algebra on this, I'll let you check this. We get that ri is equal to ri plus 1 plus 2i plus 1. And that establishes the inductive hypothesis for the next round. So that proves this claim. Now I'm going to erase the proof of the claim and use the claim to finish up the proof of this statement here. Proof goes away. There it goes. Now we can figure out the value of ri by starting with rn equal to 0 and working backwards. So we have rn equals 0, rn minus 1 is equal, using this claim, to 0 plus 2 times n minus 1 plus 1. Rn minus 2 is equal, using the claim again, to that value plus 2 n minus 2 plus 1, and so on. And in general, r sub n minus I is going to be equal to the sum from j equals 1 to I of 2 times n minus j plus 1. This is at most the sum from j equals 1 to n of 2 times n minus j plus 1. And simplifying, this is equal to n, that's pulling out this one term here, plus 2 times the sum from L equals 0 to n minus 1 of L. And here I've switched the order of summation, so I've turned n minus j into an L. And I've changed the indexing from j going from 1 to n to L going from 0 to n minus 1. But now this whole thing is exactly equal to n squared. So that means that for any I, r sub n minus I is equal to n squared, or alternatively, for any I, r sub I is equal to n squared, and that's exactly what we wanted to show. So that proves this lemma. Finally, we can prove the whole theorem. So up here, I've written what we know so far. Okay, so the first statement of the theorem we are already good on. That says that if phi is not satisfiable, the algorithm will return not satisfiable. And we just spent this whole video on the second bullet point, the case that phi was satisfiable. So in this case, we want to show that the algorithm will return a satisfying assignment with probability at least 1 minus 1 over 2 to the c over 2. So to see why that's true, let's write the probability that we fail to return a satisfying assignment. That's the same as the probability that none of x naught, x1, ... up to x sub cn squared are equal to n, which by the fact that y sub t is always at most x sub t is less than or equal to the probability that none of y naught, y1 up to y sub cn squared are equal to n. At this point, we can consider breaking up these cn squared random variables into c over 2 chunks, each of size 2n squared. I just realized that because of my indexing, there's actually cn squared plus 1 variables here instead of cn squared. Ignore that, it only makes it better for us. Sorry about that. Okay, but in any case, let's write this as the probability that none of y naught up to y 2n squared minus 1 are equal to n times the probability that none of y 2n squared dot 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 to y 4n squared minus 1 are equal to n conditioned on y sub 2n squared minus 1 times dot dot dot, and I'm going to keep on going, and there's going to be c over 2 factors in this product. So c over 2 terms live in those dot dot dots. But another way to write this is that this is equal to the probability that the minimum over t, so that yt is equal to n, is at least 2n squared times the probability, same thing, the minimum of t such that y sub t is equal to n is at least 2n squared, conditioned on whatever value of y 2n squared minus 1 was here. Sorry, I just realized I made a little righto there. 2n squared minus 1 times dot dot dot. And what we just showed here in our lemma is that the expectation of this random variable is n squared. And same for this one, and same for all of the ones in the dot dot dots. So the probability that it's greater than twice its expectation is, by Markov's inequality, at most a half. So that means that each of these terms is at most a half, and there's c over 2 terms. So this is going to be less than or equal to 1/2 to the c over 2. And that's exactly what we claimed here. Because again, this here is the same as the probability that the algorithm fails to return a satisfying assignment after cn squared steps. So that's it. That wraps up the proof of this theorem. Check. And that proves that our randomized algorithm for 2SAT works with high probability. Hooray! It turns out that it's possible to extend these ideas to 3SAT, although of course we're not going to get a polynomial time algorithm since 3SAT is NP-hard. I'm not going to talk about that in the videos, but you can check out the lecture notes if you're curious to learn more. That's all for now. Thanks for watching.